Hello everybody, we will start the study of Chapter 4, Allocating Resources over Time from this section. There are two objectives for this chapter. The first one is to explain the concepts of compounding and discounting and future value and present value. The second one is to show how these concepts are applied in making financial decisions. At first, let's study the compounding. I would like to ask you a question. Have you ever deposited some money into a fixed-term account in a bank, no matter whether you did or not? Let's see an example. Suppose you put $1,000 into an account earning an interest rate of 10% per year, and assume that you will have this account in 3 years with taking nothing out. So you deposit $1,000 into an account today. What's the final value, or in other words, the future value of this account? The process of going from today's value or present value $1,000 to its future value is called compounding. Let's define some terms more precisely. Present value. PV is the present value or beginning amount in your account. In this example, it's $1,000. I stands for the interest rate, usually expressed in percent per year. Here is 10% per year. N stands for the number of years the account will earn interest. Here is 3. FV is the future value at the end of n years. The process of going from PV to FV is called as compounding. Other two terms, simple interest and compound interest, are also referred in the calculation of the future value. The interest on the original principal is called simple interest. Here, the original principal is $1,000. The interest earned on interest already paid is called compound interest. In summary, in this example, the PV is $1,000 and its interest rate is 10%. Let's calculate the future value FV step by step. At the end of the first year, we will have the original $1,000 plus the interest of 1,000 multiplied 10%, which is equal to 100. And the $100 is a simple interest. Therefore, the PV at the end of the first year is $1,100. If we redeposit this entire sum, $1,100 for another year, during the second year, we will earn 10% interest on the entire $1,100, which is the FV at the end of the first year. So at the end of the second year, the FV is equal to 1,100 multiplied 1 plus 10%, that is $1,210. Among the interest, $210, the simple interest is 1,000 multiplied 10% multiplied 2, which is equal to $200. And the rest interest, $10, is the compound interest, which is equal to the interest of the first year, $100 multiplied 10%. At the end of the second year, we deposit again. And at the end of the third year, the FV is equal to 1,210 multiplied 1 plus 10%, which is $1,331. Among the total interest, $331, the simple interest is $300 and the compound interest is $31. Actually, in practice, we do not care about how much is simple interest and how much is compound interest. All we really care about is the FV. More direct way to calculate the FV is that at the end of the first year, the original principal or the PV $1,000 multiply 1 plus the interest rate 10% to the first. At the end of the second year, FV is equal to the PV multiply 1 plus 10 to the second. And at the end of the third year, FV is equal to the PV multiply 1 plus 10 to the third. More generally, a compound amount factor is defined to compute the FV from a present value. That is, the FV at knowing present value PV, interest rate I, and the number of compounding periods N can be calculated by the formula PV multiply 1 plus I to the nth. And the 1 plus I to the nth is defined as future value factor for any present value invested. A quiz is given here to practice the calculation in compounding. If the PV is $10,000 and the interest rate is only 3% per year, the first question is, what is the future value after 3 years? By the compound amount factor, FV is equal to PV 10,000 multiply 1 plus interest rate 3% to the nth. Here N is 3. It's found that the FV is $10,927.27. The next question, what are the simple interest and the compound interest? Simple interest is the interest on the original principal $10,000. It's 10,000 multiply the interest rate 3%, and then multiply the number of year 3. It's $900. The compound interest is equal to the FV minus the original principal and simple interest, and is obtained as $27.27. The following is another example. In the year 1926, a tribe got cash $24, and if they invested it to earn 6% per year compounded annually, how much would they have had in 2006, which is 380 years later? So PV is $24, interest rate I is 6%, and the number of years N is 380. By the compound amount factor, FV is equal to 24 multiply 1 plus 6% to the 380th. Obviously, a calculator or a table about future value factor is required. Well, if we do not have calculator or a table, how can we get the future value? Is it possible? The answer is yes. There is a handy rule of thumb that can help us estimate future values. It is called the rule of 72. This rule says that the number of years it takes for a sum of money to double in value, or the doubling time, is approximately equal to the number 72 divided by the interest rate expressed in percent per year. That is, the doubling time is equal to 72 over the interest rate. In order to understand this rule of 72 better, let's see an example. Suppose that your original principal is $1,000 and the interest rate is 10% per year. The doubling time is 72 over 10 and is equal to 7.2. So you will have $2,000 after 7.2 years and have $4,000 after 7.2 multiplied 2, that is 14.4 years. And how long will it cost to get $8,000? It is 7.2 multiplied 3 and is 21.6 years. How about the effectiveness or accuracy of the rule? Let's discuss it by an example about saving for old age. Suppose that you are 20 years old and are considering putting $100 into an account paying 8% per year for 45 years. How much will you have in the account at age 65? In summary, the PV is $100, the interest rate is 8% per year, and the number of years N is 45. By the compound amount factor, the FV is equal to 100 multiply 1 plus 8% to the 45th and is $3,192.04, rounded off to the second decimal place. Well, if the interest rate changes to 9% per year, the FV becomes $4,832.73. This suggests that a small increase of 1% in the interest rate results in an extra $1,640.69 after 45 years. And this is more than a 50% increase. Now apply the rule of 72 to this example. When the interest rate is 8% per year, the doubling time is equal to 72 over 8 is 9 years. Then after 45 years, it would double 5 times. PV multiplied 2 to the 5th. The future value is $3,200. The difference between the FV calculated by the rule of 72 and the one by the compound amount factor is 3,200 minus 3,192.04. The difference, $7.96, suggests that the approximate future value by the rule of 72 is not far from the exact answer. Besides, at the interest rate 9% per year, the doubling time is 72 over 9, is 8 years. So the $100 would be doubled about 5.5 times. Therefore, the future value should be about 50% greater than that at the interest rate 8% per year. This is also not too far from the exact answer. In conclusion, this example suggests that the rule of 72 can help us to find a pretty good approximate future value. In summary, we have studied what's compounding and the calculation of future value by the compound amount factor and the rule of 72 in this section. That's all about this section. Bye.